All right, read through this problem. Let's start drawing a rough sketch here. All right, so this big cylindrical ride, people are standing originally on a floor that does not exceed the back, but as this ride starts to rotate, it rotates faster and faster until it reaches a 0.6 revolutions per second. When it is rotating that quickly, the floor drops, yet the people stay pinned against the wall. They stay in place against the wall. We are looking for the minimum coefficient of static friction required for the person to not slide down to the floor. So circular motion, the direction, these people, their velocities is constantly changing. I have drawn my person on the left side. So from this specific vantage point towards the center is towards the right. So the acceleration this person would be experiencing at this moment would be towards the right. Now, I do want to draw a full free body diagram. The force that actually points to the right is the normal force. The wall of this ride is pushing on this person's back. So that is the normal force. There, of course, is the force of gravity. But to keep the people from sliding out of the ride, there needs to be a force of static friction upwards. And so this is what my free body diagram would look like. If there was no friction, gravity would take over and pull the people down to the floor. The acceleration, I'm just going to draw near my free body diagram. So in my picture, it points to the right. According to my free body diagram, it is the normal force that is the net force in the radial direction. So it is the normal force that is actually causing this centripetal acceleration. The wall is in the way. The wall is not allowing the person's body to continue in a straight line. Now, in terms of relating this to a speed, I'm going to plug in r omega squared, simply because they've given us a 0.6 revolutions per second. I know there are 2 pi radians in a revolution, so this is going to give me 1.2 pi radians per second. This is my omega value. Since they give us omega, I'm going to go ahead and plug in the acceleration as r omega squared. All right, we have the radius. We do not have a mass. We have omega. And so really we need to figure out where to go from here. Since they're asking us for the coefficient of static friction, I want to do something with the friction force. The friction force is in the y direction, so up and down. We know we don't want these people sliding up or down the wall, and so there is no net force in the y direction. So if we consider the forces in the y direction, the static friction force keeping them from sliding down the wall is balancing out with the force of gravity. We are talking about the biggest the friction force can be. So we are going to substitute in the coefficient times the normal force. But the radial direction has told us that the normal force is going to be the mr omega squared. So bringing these together, the mass of the person ends up canceling out. We're trying to find mu, so the value, the smallest possible coefficient of static friction, is what we're going to calculate here. I'm getting 0.28. Unit-wise, G is in meters per second squared, R is in meters, omega is 1/seconds, but we're squaring that, so both the numerator and denominator end up with meters per second squared. So we end up with no units. This number for static friction is on the lower end in terms of saying that friction coefficients lie between 0 and 1. So 0.28 would be on the smaller end, meaning most clothes against the wall should be fine. This one, I like this one. Partially because we get something unexpected. The normal force is what's creating this centripetal acceleration. And then we still have to look at forces in the y direction to relate all these forces together. But the approach is the same. Free body diagram, write out what we mean by net force equals mass times acceleration in the different directions. So the approach is similar to what we've been doing all along.